Okay, so the last two sections of this chapter, 2.7 and 2.8, are all about solving inequalities. So we've talked about solving equations, graphing functions, and things like that. But one of the things that we're going to want to be able to do as well as we move through the course is to be able to solve inequalities. And again, this is something that you have seen in your algebra career, I guess. So we're just going to um, briefly review it. So I think back in chapter 1, we talked about solving linear inequalities. So we're already pretty good at that. What I've done is I've split the inequalities portion of the material into two parts. And in this first part, we're going to cover radical and absolute value inequalities. And then in 2.8, we're going to talk about polynomial and rational inequalities. So, as we saw in chapter 1, we can solve linear inequalities the same way that we solve linear equations. But this is not always true for nonlinear inequalities, like polynomial, rational, and radical inequalities in particular. So, looking at radical inequalities, a radical inequality would, of course, be an inequality that involves a radical like this thing, right? Square root x plus 7 plus 5 is less than or equal to 8. If we try to solve this the way that we would solve the corresponding equation, like if we just pretended that this inequality were an equation, then we would move the 3 over and then square both sides and then move the 7 over, and we would see that x is less than or equal to 2. But there's a slight problem there, because if x is less than or equal to 2 is the solution set, then that would imply that something like x equals negative 11 could be a solution. But if you plug in negative 11, right, square root of negative 11 plus 7 is, well, that's the square root of negative 4, which is 2i, and that's not even a real number. So that can't be a solution, because what you would get here would be 2i plus 5 is less than or equal to 8. And that's really a nonsensical statement, because you can't order the complex numbers the way that you can order the real numbers. Like, it doesn't make sense to say 2i plus 5 is less than or equal to 8. So, so as far as radical inequalities are concerned, it's okay to solve them the way that you would solve the corresponding equation, but then you also have to take into account what the domain of the radicand is, or rather, what the domain of the radical part of the inequality is, right? So we proceed as if we're solving a radical equation, but we make sure that we exclude any values from the solution set that would yield non-real results. So the solution set for a radical inequality with an even index will be the intersection of the interval that satisfies the inequality and the interval where the radicand is non-negative, right? So if the index here is even, then we need the radicand to be non-negative. In other words, we need it to be bigger than or equal to 0. If, on the other hand, the index is odd, then there are no additional restrictions. We just solve that just like we would solve the corresponding equation. So let me walk you through several examples. This one says, it says use Desmos to verify your solutions. So we'll take a look at some of these things in Desmos. But let's solve this thing. So first of all, I'm going to solve it the way that I would solve the corresponding equation. So I would move over the 2. Then I would square both sides, move over the 10, and divide by 5. Okay. But then I have the additional restriction that I need for the radicand to be positive. Since I have an even index here, I need the radicand, 5x plus 10, to be bigger than or equal to 0. Okay, so I need both of these conditions to be met, right? So now let's say 5x has to be bigger than or equal to negative 10, so that x has to be bigger than or equal to negative 2. So I need for x to be less than 3 and for x to be bigger than or equal to negative 2. That means x has to be between negative 2 and 3, including the negative 2, not including the 3. Now, if you have a hard time jumping straight to the interval, then you could make a little graph of this thing. And on the one hand, we need for x to be less than 3. And then on the other hand, we need x to be greater than or equal to -2. And since this is an and inequality, that means we're going to take the intersection of these two sets. The intersection is the overlap, right? So that's all the stuff from -2 to 3, including the -2, not including the 3, right? So that's the idea there. You don't have to draw the graph unless it's helpful to you, right? Or unless I ask you to draw the graph, right? But that's the idea. Now, to verify this in Desmos, let's take a look. So let's do square root 5x plus 10, and then plus 2 on the one hand, and then we'll do just 7 on the other hand. Oh, maybe I need to say y equals 7. No, it doesn't want to do that. Maybe I'll say f of x equals 7. Oh, there it goes. Okay. So, so if we want to solve, so we're looking for where this thing, the red curve, is less than the blue curve. So in other words, where it's underneath the blue curve. Well, it's underneath the blue curve as long as x is less than 3, right? As long as x is less than 3, but of course bigger than or equal to -2, right? Because the function doesn't even exist over here. I mean, it exists, but the outputs are non-real, so they don't show up. Right? So that confirms our suspicion that the solution set is -2 to 3, including the -2, not including the 3. Okay, let's look at another one. All right, so same thing, move the 4 over. And then divide by the negative. And then square both sides. Finish solving. You get x greater than or equal to 4. Okay, so on the one hand, x has to be greater than or equal to 4. Now on the other hand, we need for 2x plus 1 to be bigger than or equal to 0, right? We need the radicand to be non-negative. So solving this one, we see that x needs to be bigger than or equal to -1/2. If we make a graph of this solution set, we get this scenario, right? We need x to be bigger than or equal to -1/2, and we need x to be bigger than or equal to 4, right? Right? We need both of the conditions to hold, so we need to look at the intersection. The intersection section is where they overlap. They overlap from 4 onward, right? So from 4 onward. So the solution set in this case is going to be 4 to infinity. Okay. We can verify that in Desmos as well. So I'm going to do 4 minus square root of 2x plus 1. And then I'm going to do 1. Oh, I have to say, I think y equals 1 or something like that. Okay, we're looking for where the green is less than or equal to the red. So we're looking for where the green is underneath the red. That happens from 4 onward, right? So it happens from 4 onward, just like we suspected here. Okay, let me give you one more of these, right? So cube root x minus 7 is greater than or equal to 3. Since this is an odd index, we don't have any further restrictions. Like we don't have to set x minus 7 greater than or equal to 0, because we're going to get real outputs whether this is positive or negative, okay? So this one we just solve like we would solve the corresponding equation, and that's all we have to do. So cube both sides, and then add the 7 And that's it. Right? No additional restrictions here because the index is odd. And we can verify that as well if we want. So let's go back to Desmos. I'm going to have, I don't know how to type in cube root. Maybe I'll have to use, well, maybe I'll just use to the 1/3 power. How about that? So I'm going to say x minus 7 to the 1/3 power. Okay, and then I want to compare that to, let me get rid of these guys. And then I want to compare that to y equals 3. And so we're looking for where the blue curve is greater than the green curve. So we're looking for where the blue curve is above the green curve. That happens right here at 34, just like we thought, right? You can hear my dogs going crazy because somebody just got here. Anyway, so from 34 onward, right? And that's exactly what we discovered doing this. So that's how these things work. That's how radical inequalities work. Let's talk about absolute value inequalities. So first thing that I'll point out is that note that if the absolute value of x is less than 2, then that means if you think about the absolute value in terms of its distance from 0 on the number line, then if you're saying the absolute value of x is less than 2, then you're saying that x has to be within 2 units from 0, right? It can be no more than 2 units away from 0 on the number line. So the picture would look something like this, right? -2, 0, 2, right? X would have to live in here, right? In other words, x has to be between -2 and +2. So this statement here corresponds directly to that statement. On the other hand, if absolute value of x is greater than 2, then that's saying that x has to be more than 2 units from 0 on the number line. And that also can happen in, well, not also, but that can happen in 2 ways, right? That could happen, you're going to be more than 2 units away from 0 on the number line if you're here or if you're here, right? So x has to be less than -2 or x has to be greater than +2, right? So this statement here corresponds to that statement. They're equivalent statements. So in general, we can make the following observation, right? Anytime you have absolute value of some function of x, if that is less than a, then that means that the stuff inside the absolute value is sandwiched between -a and +a. That's if a is a positive number. If a is a negative number and you have something that says absolute value of something is less than a negative number, that's not possible, right? That has no solution because the absolute value is going to make the thing positive. So it can't be less than a negative number. If f of x is great, absolute value of f of x is greater than a, then that means f of x must be greater than a, or f of x has to be less than -a. Okay, because it has to be more than a units away from 0 on the number line. Again, that's if a is a positive number. If a is a negative number, then every real number in the domain of f of x is going to be a solution to this, right? Because if a is a negative number and you take the absolute value of, you know, this function, then of course you're going to get a positive number, and of course that's going to be bigger than a. Right, so the solution set to this sort of thing is all reals if a is negative, right? So really we have these 2 cases, right? These are the 2 important ones, right? If you assume that a is a positive number and you have absolute value of f of x is less than a, that means f of x is between -a and +a. If you have f of x is greater than a, that means that either f of x is, sorry, if you have absolute value of f of x is greater than a, that means f of x is greater than a, or f of x is less than -a. These other 2 cases are just kind of special cases when you happen to have a negative number on this side of the inequality. So when you have a negative number on that side of the inequality, just take a second to think about the scenario, right? But you're either going to have no solution or all reals as your solution set. So let me walk you through some examples, right? Here we have absolute value 3x plus 2 less than 8. So that's like this first case, right? We have absolute value of something is less than a, and a is positive. So we're going to apply this rule. We're going to say, well, then the stuff inside the absolute value should be sandwiched between the negative version of this number and the positive version of this number. In this case, the number is 8, right? So we would say negative 8 is less than 3x minus 2, which is less than 8. This one we just finished solving. You know, this is just a linear inequality now. So we can add 2 everywhere and then divide by 3. And there you go. Our solution set is negative 2 to 10/3. And that's all there is to it. Part B, on the other hand, is not a case 1, it's a case 3 example, because you have absolute value of something is greater than some positive number. So that's like a case 3 scenario, right? First of all, before we apply this case 3 rule, let's finish isolating the absolute value. So I'm going to divide by 2. And now I'm going to say, all right, so the stuff inside the absolute value, if the absolute value of x plus 5 is greater than or equal to 6, that means that x plus 5 has to be more than 6 units away from 0. So that means that either x plus 5 is greater than or equal to 6, or x plus 5 is less than or equal to negative 6, right? So those are the two cases, x plus 5 greater than or equal to 6, or x plus 5 less than or equal to negative 6. And then we finish solving these linear inequalities. So we get x has to be greater than or equal to 1, or x has to be less than or equal to negative 11. In other words, right, well, let me draw a picture maybe on this one. It'll be a little bit more clear. So if negative 11 is there and 1 is there, x less than or equal to negative 11 means this. X greater than or equal to 1 means this. And or means union, right? We're going to take the union of these two things, not the intersection. If we were taking the intersection, then this would be no solution because there is no overlap, right? But this isn't the intersection, it's the union. We're just going to combine the two sets together. So this first interval is negative infinity to negative 11. The second interval is 1 to infinity. And we're going to take the union of those two, and that's our solution set. Okay? So that's it for part B. Let me walk you through a couple more. Okay, so here's another one where the absolute value isn't isolated. You have to isolate the absolute value before you apply the rules on the previous page. Okay, so you have to have something that says absolute value of f of x is, you know, greater than a, or absolute value of f of x is less than a before you can apply the rule on the previous page. So in this case, we need to isolate the absolute value first. So I'm going to do that by subtracting 3. And now I see that I have a situation like this first thing, right? If absolute value of 2x plus 1 is greater than 7, then that means 2x plus 1 has to be more than 7 units away from 0 on the number line. So 2x plus 1 would have to be greater than 7, or 2x plus 1 would have to be less than negative 7. Okay, so then 2x is greater than 6 and x is greater than 3, or 2x is less than negative 8 and x is less than negative 4. Okay, negative 4, 3, there's x greater than 3, there's x less than negative 4. The solution set, negative infinity to negative 4, union 3 to infinity. Okay. My kids are going crazy. Let me correct something on the previous page. I apologize. Coming back here, I shouldn't have used parentheses. I should use brackets, right? Because the 11 here is the negative 11 here is included, and the 1 there is included. So so I apologize for that. These should be brackets. But these ones should be parentheses because the negative 4 and the 3 are not. They should not be included in the solution set. My apologies. Okay, one more, part D. So first step, isolate the absolute value. So we're going to subtract the 4 and then divide by 3. So now we have a statement that says absolute value of x minus 7 is less than or equal to negative 2/3. That's not possible, right? Anytime you have a negative number, after you've isolated the absolute value, if you end up with a negative number over here, you need to pause. That should give you pause, okay? So what this is telling us is that the absolute value of some number, which has to be positive, is less than or equal to a negative number. Not possible, right? That's just not possible. There's no solution to this inequality, okay? And that's that. So that's how sort of these simple absolute value inequalities work. But as we saw in section 2.1 when we were solving absolute value equations, we know that they can get a little bit more complicated than this, okay? So if the inequality does not have one of the forms listed above, then we need to appeal to the piecewise definition in order to work out our solution, okay? Oh, and this is a little tricky. I'm a little rusty on these, so bear with me. I might make some mistakes. But let's see if we can solve this inequality. So the first thing I would do is I would try to simplify it a little bit. Like I know that, for example, I can move the 2x over, and then I get absolute value of x minus 3 is less than or equal to 2x plus 2. And then that's about as good as I'm going to be able to do, right? So what I need to do now is appeal to the piecewise definition of this absolute value thing. Because on this side of the equation, I've got an x still. It's not just a number, right? So it's not like one of the cases on the previous page. So I really need to think about this x minus 3. So absolute value of x minus 3, let's remind ourselves, the piecewise definition of this is that absolute value of x minus 3 is x minus 3 if x minus 3 is bigger than or equal to 0, or it's negative x plus 3 if x minus 3 is less than 0. I think usually I rewrote these the other way around when we were doing the piecewise definition earlier, but it doesn't matter. This is the same thing. So let's see. This would be x minus 3 if x is greater than or equal to 3, and negative x plus 3 if x is less than 3. So the place where this changes rules is at 3. So I'm going to look at two different cases. I'm going to say, well, if x is less than 3, then absolute value of x minus 3 would actually be negative x plus 3. And then we get the statement negative x plus 3 is less than or equal to 2x plus 2. If, on the other hand, x is greater than or equal to 3, then I would use the top rule, and I would say absolute value of x minus 3 would just be x minus 3. And we get x minus 3 is less than or equal to 2x plus 2. And now I've eliminated the absolute value from the inequality, so I can just finish solving these like a normal inequality now. So I would move the 2x over, move the 3 over, divide by negative 3. Because I'm dividing by a negative, the inequality has to switch directions. So I get x greater than or equal to 1/3. Over here, move the 2x over. Oh, sorry. Let me try that again. Move the 2x over, I get negative x minus 3 is less than or equal to 2. Add the 3 over, I get negative x is less than or equal to 5. Divide by negative 1, I get x greater than or equal to negative 5. Okay. So how do I make sense of this? A good thing to do would be to maybe draw a picture. So I'm going to draw a picture that attempts to describe everything that's going on. So I should definitely put 3 on there. And I should definitely put negative 5 on there. And I should definitely put 1/3 on there, since these are all kind of key players here in what we have going on, right? So on the one hand, if x is less than 3, then I need for x to be greater than or equal to 1/3. So that means just from this first rule, my solution set is looking something like this, right? Because I need both of these conditions to be met. I need x to be less than 3, and I need x to be greater than or equal to 1/3, right? So that's this first solution set. The other possibility is that I need x to be greater than or equal to -5, and for x to be greater than or equal to 3. So I need x to be greater than or equal to -5, right? All of this stuff. And I need x to be greater than or equal to, sorry, greater than or equal to, and I need x to be greater than or equal to 3. So that's going to be the intersection of those two things, right? So my other solution looks like this, right? From 3 to infinity. So from 3 to infinity. So on the one hand, I have one solution set that looks like 1/3 to 3, not including the 3. And then I have another solution set that is 3, including the 3, on to infinity. And either one of these rules could be true. And so whenever you see an or, that corresponds to a union. So I'm going to take the union of these two sets. The union of those two sets is the combination of those two sets, right? So the union of those two sets is just going to be 1/3 to infinity, including the 1/3. So I suspect that the solution set here is 1/3 to infinity. Let's use Desmos to see if I'm right. So we want to do, let me just put in the original, 2x plus absolute value x minus 3 on the one hand, and then on the other hand, 4x plus 2. Okay, ooh, so this is crazy, but we're looking for where 2x plus absolute value x minus 3 is less than or equal to 4x plus 2. In other words, we're looking for where the purple stuff is less than or equal to the black stuff. So where the purple is underneath the black. So this is where it crosses. I'm going to guess that's 1/3, right? So 1/3. So they cross each other at 1/3. And then from that point onward, it looks like the purple is less than the black. It's underneath the black. And it's the difference, they're just getting further and further apart the more we go out. So that confirms my suspicion. Look at this crazy thing that happens at 3, right? That was one of our points of interest earlier. And then another point of interest was -5. It doesn't look like anything really interesting is happening there, but anyway, but there you go. So that confirms our suspicion, right? So 1/3 to infinity. So that's how you deal with these things. They're kind of beastly, but I like them at the same time, because in order to find this first little solution set, we had to take an intersection. So in order to find this second solution set, we had to take an intersection. But then to find the overall solution set, we had to take the union of those two solution sets, right? So it's like you really have to know unions and intersections pretty well. So I'm glad that we spent that time in chapter 1 talking about unions and intersections. But that's it. That'll do it for 2.7. And we'll see you in 2.8 where we'll talk about polynomial and rational inequalities.